Welcome back. Now I want to talk to you about the Rubik's Cube, which is one of my favorite puzzles too. And is there mathematics in the Rubik's Cube? Well, most people think there is, right? And most people think actually that one needs to be a genius to solve the Rubik's Cube. Today I don't want to talk about actually solving the Rubik's Cubes. There are tons of algorithms. If you Google quickly, you're going to find ways to do it, and it's a matter of memorizing certain algorithms, and then you're going to be able to solve it. What I want to talk to you about is, can we always solve a Rubik's Cube? And what do I mean by that? Well, you can imagine that if you take a Rubik's Cube, you bought it, right? It's in the solve position. You move it, you move it in all possible ways, and you keep moving it. Then that whatever state you get to, you should be able to solve it back to make it into the original position by reversing those moves. And that shall not be surprising. But what about if I take the cube apart, I take all of the different cubies of the cube apart, and mix them, and put them back together. Well, notice that corners have three faces, so if you realize that any corner will have three faces, as you have here in the video. And edges in here have two faces. Okay, so these two. So if you take the cube apart and put it back together, you put corners in corners, edges in edges. The middle ones, the middle cubies, actually don't move. They're on a fixed axis. You cannot remove them. So let's say that you take all the corner and edges apart and put it back together after you mix them. You're gonna get a cube, it might look like this. It's going to be all scrambled. And the question is, can you solve that? What do you think? Can you solve it? The answer is not always. So it depends. And we actually know what the chances are that you can solve it. So let's go ahead and talk about it and how mathematics is used for that. So again, let me be clear on what I mean by solve it. By solve it, I mean that you can use one of the 12 basic moves. So these are, you can do right face, front face, you can move it, you can move the left face, the back face, the top and the bottom. And you can move them either 90 degrees clockwise or 90 degrees counterclockwise. So for each of the 6 faces, you have clockwise and counterclockwise. So those are the moves that we use. And what strategy can we use to check if we can solve this? Well, one is find all possible ways. Again, this is brute force. If you watch the Sudoku puzzle video, the brute force is check all possible ways. So, in how many ways can we take apart the cube and put it back together? How many different ways can I put it back together? Check all of them and check if I can solve them. Well, how many ways is that? Think about the following. So there are 8 corner cubies. If you actually let me go into this slide. So there are 8 corner cubies. The ones on top and the bottom. All of the 8 corners of a 3x3x3 cube. And those so those can be permuted in a factorial ways. And then each corner has 3 possible orientations in which it can be in. So you can take that corner piece and rotate it and put it back. Rotate it and put it back. Rotate it, put it back. There are 3 ways that you can permute the 3 corners. So the corner cubies can be rearranged in 8 factorials times 3 to the 8 different ways. The edge cubies is the same idea. There are 12 of them, 12 factorial ways where you can take them apart and put them back together. And then each of them has 2 orientations. You can think, for instance, in here, red on top and white on the right one, or white on top and red on the right one. So there are 2 for each. And again, the center cubies, they're fixed. We're not going to move them. They're on a fixed axis. So if you take that computation, it is 519 quintillion different ways that you can rearrange the Rubik's Cube. That's a lot. You cannot check that many in a computer. It's just, we don't have the computation power to do that. It's too many. So the brute force approach doesn't really work. We have to use some mathematics. And this is where modular arithmetic and just some mathematical analysis comes in play. The key idea that we're going to be using is an idea which is to label the corner, well, label all cubies, but I'm going to show you the corner ones. Label the corner cubies using the numbers 0, 1, and 2. So, for instance, in here, you see that this corner cubie is labeled 0, 1, and 2, and it goes sort of like clockwise. And this one again, 0, 1, and 2, and it's labeled clockwise. So we're going to do that. So for instance, one way to do it is take this space with the blue center, and you're going to take the corner cubie that's in there in the solve position. So this labeling, it's easier to see in the solve position. In fact, let me actually show it to you in my cube in here. And I'm going to do it using white. So I'm going to take the white face and be the one on top. And in the solve position, when this is in the solve position, when all of these cubies are white, I'm going to put a 0, 0, 0, 0 on top. Okay, so 0, 0, 0, 0 on top. And then I'm going to complete the labeling for each corner cubie by going clockwise 1 and 2, 1 and 2, 1 and 2. Okay, so 0 on top, and then 1s and 2s are going clockwise around that. And then I'm going to do the same thing on the yellow bottom. So I'm going to put 0, 0, 0, 0 when this is in the solve position, when all of them are yellow. And I'm going to complete them 0, 1, and 2 clockwise. Okay? So always in the solve position, the top corner cubies in the top face are 0, and the bottom ones in the bottom face are 0. And then, okay, so that I can do that. And then as I move the cube, of course, those numberings are going to move around. So for instance, in this picture that you have, you see that in the top white, you no longer have a 0 on top because you move the cube. So as you make moves, these numbers are going to go around. But one can check that once you had all the zeros in here, in the solve position, if you make any of the 12 basic moves, any of them, when you look at the numbers that appear in the top and the bottom face, they're no longer going to be 0, 0, 0, 0, 0, 0, 0, 0. They're no longer going to be all the 8 zeros. And that you can see because as you make a move, right, you're going to take these zeros that were here, and they're going to move, and you're going to get some new numbers on top, right? If these two were 0, when you move them, you're going to get new numbers on top. But what does happen is that the numbers that you get always add up to 0 modulo 3, okay? So the numbers that you get in the top face and the bottom face, it doesn't matter which move you make, when you look at the top face and the bottom face and you add the 8 numbers that appear in the top faces and the bottom faces, they always add up to 0 mod 3. That's interesting. That means that any valid configuration, any configuration you can get from the starting position, will have, under this labeling, a sum of 0 mod 3 in the top and the bottom. When you look at the 8 faces on the top, the 4 corner faces on the top and the 4 corner faces on the bottom, they're going to add up to 0 mod 3. That's quite interesting. The reverse is also true. If somehow you have, someone gives you a scrambled Rubik's Cube that was labeled in this way originally, so which you can always figure out what that labeling is, because you can think of, oh, what should be the corner cubie here when it's solved, and you put a 0 there, and so on and so forth. So you can always label a scrambled cube in this way. You can check if the sum of the corner cubies is 0 mod 3. If it is, there's a way to put them back in their original position. If it's not, there's no way to do it. Okay, and this you can show by actually by using a little bit of combinatorics combined with abstract algebra. So what we can conclude from this is that if you label the cube in this way, the sum of the faces of the corner faces in the top face and the bottom face have to be 0 mod 3. They have to be a multiple of 3. And one can check that out of all possible configurations, if you break the cube apart and put it together, a third of them have a sum of 0 mod 3. Because there is an equal chance that you're going to get a sum of 1 mod 3 or 2 mod 3. If you consider all possible ways you can break the cube apart and put it back together, a third of them will have a sum of 0 mod 3 once you add the top corner faces and the bottom corner faces. You can do a similar argument to the edges. So if you label the edges in the solve position, you're going to get the four edges on the top, the 4 edges on the bottom, and then the two faces of the edges on the right and the two faces of the edges on the left. You label them as 0 in the solved position. And you look at those 12 faces. It doesn't matter what move you make, their sum is always 0 mod 2. So, and the reverse is true. If someone gives you a scramble cube and you label it in this way, then if when you add the edge faces on the top, there are 4 of them on the top, the numbers that are there. The edge faces on the bottom, the 2 on the right and the 2 on the left, then they have to add to 0 mod 2, and if they do, then you can put these edges in the right place. Now, one thing is to be able to put the corners where they're supposed to go, put the edges where they're supposed to go, but can you do it together? Well, we need one more condition. Oh, and let me say that half of the total configuration satisfy that. So you can think of, if you break the cube apart and put it back together, half of them, when you look at those 12 faces, will add to 0 mod 2. The other half will add to 1 mod 2. And then another property has to be true for you to know if you're able to solve the Rubik's Cube. And that is that when you think about the corner cubies, there are 8 of them. And if you start with the solved Rubik's Cube, then we're going to call the position of the 8 corner cubies to be in their identity position. So the corner cubie, so like let's say that we labeled this as our corner number 1. Well, in the solved position, we're going to say that the cube that's supposed to be there when it's solved, it is there, so 1 goes to 1. If this is corner cubie 2, 2 goes to 2, 3 goes to 3, 4 goes to 4. The same thing on the bottom. But if you scramble it, then you can see where did 1 go. Maybe 1 go to corner 2. So if that happened, then we are going to say that that 1 went to 2. And you can sort of like look at where all of the 8 corner cubies are located. That's going to give you a permutation of 8 objects. You can do the same thing with the edge cubies, where the edge cube is located. That's going to give you a permutation of the edge cubies. And one can check, so any one move, so for instance, let me try this one. Any one move, what it does is it takes, for instance, this 4 corner cubies, the 4 corner cubies in this phase. If I do one move, they're moving in a 4 cycle. This one moves down here. The one that was here moves here. The one that was here moves here. The one that was moving here moves here. So it moves in a 4 cycle. And the same thing for the edges. They move in a 4 cycle. Right? Every time you do a move, they move in a 4 cycle. It doesn't matter which move you make, they move in a 4 cycle. Both the corners and the edges. And a 4 cycle is an odd permutation. You're going to learn that. And a 4 cycle can be written as a product of 3 transpositions, which makes that an odd permutation. So any move of the Rubik's Cube moves the corner cubies in an odd manner, so it's like as an odd permutation, and does the same thing with the edge cubies. So regardless of the position that you're in after you move the cube several times, if you make n moves, then you make n 3 cycles on the corners and n 3 cycles on the edges. So when you look at the positions of the corner cubies, they are going to be a 4 cycle a product of n 4 cycles. And if you look at what happens to the edge cubie, it's going to be a product of n 4 cycles too. So when you look at the permutation of the corners, if that permutation ends up being odd, like for instance when you do just one move, it was just 1 4 cycle, the same will be true for the edges. The permutation of where the edges are located is also odd. If you do like 2 moves, then it's a 4 cycle times a 4 cycle. That's an even permutation for the corners, but it's also a 4 cycle times a 4 cycle and even permutation for the edges. So when you look at where are the corners and edges located, and you write it down as a permutation, the permutation for the corners has to have the same parity as the permutation for the edges. So either they're both odd or they're both even. Now if you break them apart, for instance, if you break the cube apart and switch 2 corner cubies and put them back together, that's going to damage the parity of the corner cubies permutation. So if you take, for instance, the Rubik's Cube in its solved position and you exchange just 2 corners and put them back, that will not be able to be solved because the parity of the permutations will be damaged. So one can prove that if you are given a scramble cubed and you look at where the corners are and what the edges are. If the permutation of the corners and the permutations of the edges are both even or both odd, and the sum of the edge cubies is a multiple of 0 mod is a multiple of 2, so it's 0 mod 2. And when you look at the numbers in the corner cubies, they add up to 0 mod 3. You're guaranteed that you can solve that cube, and that's an if and only if. So if it satisfies these conditions, you can solve it. If you can solve it, it satisfies these conditions. The one about the parity of where the corner cubies are and where the edge cubies are, in about half the cases, you're going to have the corners being an even permutation and the edge being in an even permutation, or both being odd. In the other half, one is even and the other one is odd. So in half of the cases, we have that condition. So out of the 519 quintillion, out of the 43 quintillion, no, I got it wrong here, sorry. Out of the 5.19 times 10 to the 20, so 519 quintillion configurations of the Rubik's Cube, only 1/12 of them, because a third of them have the right numbers in the corners, half of them have the right numbers in the edges, half of them have the same parity of the permutation of the corner cubies and the edge cubies, so a third, a half, and a half, that's a 12. About a 12 of them can actually be solved. The other 12, the other 11/12 of the configurations cannot be solved. So out of the 519 quintillion, only 43 quintillion are actually solvable. I hope you enjoyed this. There's tons more of things to say about the Rubik's Cube, about God's number of the Rubik's Cube, which actually also uses a lot of the symmetries of the Rubik's Cube to be able to be solved, about how to solve the Rubik's Cube and how do you get some of the algorithms to get them, and tons of interesting mathematics in the Rubik's Cube. So if you're intrigued by it, I suggest that you do some Google searches and find some of the interesting mathematics that's behind that. I hope to see you in the next video, so see you in a moment.